let me show you what we need to do with our copper solution that was prepared by dissolving reacting the penny. So we're going to take this strongly acidic copper ion solution and zinc and pour this into a 50 milliliter volumetric flask. Now we'll add some water to our beaker to transfer every last bit of copper ion into this volumetric flask. This is what we call quantitative transfer. We want all the quantity of copper to be transferred to this flask and none left behind. So I'm going to rinse the beaker 3 times. Okay, and now we're going to go ahead and transfer this until the water, distilled water, is 1 centimeter from the calibration mark. And then we'll aspirate, and using a dropper pipette, bring ourselves down to eye level. And we'll make sure that that's exactly 50 milliliters. As usual, invert this flask 10 times to mix things up. Now we're going to do let's transfer this into a small Erlenmeyer flask here. And we're going to prepare 3 solutions of the analyte, the thing we're analyzing. Okay, this is not part of the calibration curve. This is going to be our final concentration, that we're determining, okay, for the copper penny. Now, what you want to do is take some of your cuvettes and clean them out. The best way to do that is flush it with water, okay, if they have components in there, okay, and pull all the droplets of water out, okay? And I'll do that for these 3 here, just so you can see how that's done. Now that we have 3 clean and, for all intents and purposes, practically dry cuvettes, we'll use these for 3 determinations of this copper ion concentration. So what we want to do here is we want to pipette in 150 microliters of this solution into each of these 3 cuvettes. Okay, so dial in 150, and this will be 150 microliters of this acidic copper ion zinc ion solution. So that's trial 1. That's trial 2. And this is trial 3. Use a new pipette tip, and what we're going to do is transfer in the 15 molar ammonia. And you should be transferring in, oh wait, first we need to add a little bit of water to these cuvettes, and we're going to add in 1 milliliter, okay? So dial in to the 200 mark here, in this case, using this one, and pipette in 5 waters into each one. So that's 5 into the second cuvette. So that was 1,000 microliters of water, or equal to 1.000 milliliters. Now we can add the ammonia. What we're going to do here is add 200 microliters of 15 molar ammonia. What the ammonia does is it neutralizes the nitric acid that's left over from this chemical reaction. The copper ion will react with hydroxide to precipitate and form copper hydroxide. And then the excess ammonia will then dissolve that precipitate to form the copper ammonium complex. So it does a lot, and that's why we need such a high concentration and so much of it. So here's 200 microliters. Okay, and you can see how there was an initial precipitate, and then it went away, and it's a slight blue color now. Okay, that's what it should look like. You might think there's no copper in there because it's so faint you can't see it. But this is what it looks like. This is what it should do. You just jiggle it a little bit. Don't shake it too vigorously to splash the contents out. Okay, now we need to add some more water to this to bring the level up so that it can be inserted into this spectrophotometer. And we do that by diluting the final volume to around 3.5 milliliters. So far we've added 1350, okay, or 1,350, and we want 3,500 microliters. So it's going to be another about 2 milliliters. Okay, so I'm going to just add 2 milliliters more. So that's going to be 10 shots of the 200 microliter pipette. Okay, so 10 of these for each cuvette.
"11 minutes later."
Okay, we have our 3 trials prepared. Trial 1, trial 2, and trial 3. And as I mentioned, the final volume in each of these is 3.350 milliliters, and that was taken from a 50 milliliter aliquot. So all of the moles of copper are dissolved in this 50 milliliters, but we're only taking 200 microliters. I'm sorry, we're only taking 150 microliters of that solution to analyze. So it's going to be, of course, more concentrated in this than that just small test tube. Okay, so we're just taking a small fraction to analyze, and we have plenty to do that again and again if we mess up. Now you want to go ahead and let's once again start up our spectrometry app. The blue light's on, which means it's using Bluetooth to communicate with our iPad. Select spectrometer. It'll have a different name depending on what instrument you're using in the lab. And there's all these solutions here. You can delete these if these bother you. I'll go ahead and do that here. You can also export the data, take a picture or share it up there on the upper right hand corner. I'm just going to go ahead and delete these here, okay? Now, we're still reading 590 nanometers, and so I'm going to clean the clear faces of the plastic, insert it into here, and hit the record button on the device. It's doing 5 scans to average once again, and we're getting a value of right there on the screen, okay? And so that's trial 1, all right? Trial 2, let's do that again. Okay, that's what I'm seeing there on the screen. And let's do trial 3. Okay, and we'll go ahead and click the stop there, okay? Now, ideally, I don't have time to do this. You would want to adjust your concentration by trial and error to get it between an absorbance of, around 0.2 or something, okay? 0.15 or higher, but less than 0.3, something like that. And this is quite a bit to dilute, but we're going to go ahead and just determine the concentration from the numbers that are on this screen here, okay? That's the lab there. So next we just do calculations to figure out what is the copper ion concentration in the, what is the number of moles or grams of copper in the original penny and the percent composition, and then calculate the thickness of the copper clad penny using geometry, okay, area of a cylinder basically, okay.